Center Fellow this semester, and the title of the talk is Functional Localization in Flux in the Philosophy of Neuroscience and Cognitive Science. On Tuesday next week, David Barak, who is also a Center Fellow, will be giving a talk on neural doctrines, about the neural doctrine. So the talk will be on Tuesday at noon. On Friday next week, we do not have a lunchtime talk, but we have the third lecture in the annual lecture series given by John Fuller, my colleague in HPS, at 3:30 on the 10th floor. And the title of the talk is What's in a Diagnosis? Toward Philosophy of Diagnostic Medicine. All title to John's talk. Today, it's my pleasure to introduce Marta Bielinska, who is a Center postdoctoral fellow. She's been with us now for a few months. We've been very lucky to have Marta with us. She started her studies at Bielinska. I'm sure I'm butchering it.
It's great.
It's great. All right. That tells you everything there is to say about that. University in Poland, one of the leading universities in Poland. She got a BPhil in philosophy at Oxford, as well as a master in science in mathematical theoretical physics. And before completing her PhD at Oxford as well, she has published on a range of topics in the philosophy of topics, but also in the philosophy of religion. And I will mention two things. She won the Du Châtelet Prize in philosophy of physics. I know, that's a language I should be more familiar than Polish. The Du Châtelet Prize in philosophy of physics, and that prize led to a paper in studies in philosophy and history of science called A Philosophical Introduction to Hidden Symmetries in Physics. So congratulations for the prize, one of the leading prizes in philosophy of physics. And today, Marta will be talking about epistemology of space-time structure, a case study of space-time orientability. The floor is yours.
Thank you so much for this lovely introduction and invitation to be at the center and to give this talk to you today. It's a huge pleasure for me to speak to you. When I ask my colleagues at the center how to make a philosophy of physics talk that will be interesting to the general public, they told me that I should put in a lot of pictures and I'll be fine. And indeed, when you hear that I work about philosophy of space-time, you probably expect to see something like, oh, I can't move the... Sorry, that was the climax moment. Okay, great. I should have a cursor. Okay, so that's what you probably expect to see when I say that I work on philosophy of space-time. Further, when you learn that this project is on space-time epistemology, you probably expect to see something like this. However, that's not what this talk is going to be about at all. And just to clarify, I'm not making here a big philosophical point that while there are various ways of thinking about space-time epistemology, my way is somehow superior. And instead, I just want to make it clear that this specific story that you're about to hear isn't about telescopes, stars, or nebulae, but rather about slightly different understanding of space-time and its epistemology, which draws from relativity theory. All right, so how do we understand space-time in relativity? Space-time in general relativity, by many considered the best space-time theory that we have currently in physics, is taken to be a 3+1 Lorentzian manifold. And now a manifold is roughly a space which is locally homeomorphic to a Euclidean space. That is, we sometimes say that it is locally Euclidean. So on this picture, M is a manifold, U1 and U2 are open subsets of M, and Rn is, in this specific context, a Euclidean space. And thus, from this picture, we can see that for any such set U on a manifold, there is a homeomorphism to Rn. And in this sense, I say that manifold is locally homeomorphic. All right, but I just said that a manifold is a space. But I told you that this talk draws from relativity. So shouldn't I have said space-time instead? And indeed, the distinction between space and time is given by a metric, which here is a 3+1 Lorentzian metric. A metric roughly provides an account of the measure of distances. So here you can guess that 3 refers here to spatial dimensions, while 1 refers to the temporal dimension. Specifically, Lorentzian metric gives rise to a light cone structure. So I'm sure that it's already familiar to you. So just to recap, here we have 3 classes of vectors. We have time-like vectors that are inside the light cone. We have null vectors that are on the surface of the light cone, and space-like vectors that are outside of the light cone. And accordingly, we can think about various paths that correspond to these various regions of the light cone. So the path that will be interesting for us in this debate here is represented by an example of this red line, which is a world line, which is a time-like path. And this is a path that corresponds to the trajectories of massive objects like you, me, or electrons. So whenever we have an object that has any sort of mass that will be of interest for us later on in this talk, it will be inside the light cone, and it will be called a world line. So, all right, I think that maybe at this talk you've probably started thinking, oh my God, another very formal talk. Like she just read a few handbooks in physics. She just found this one random space-time property and she made the whole talk out of it. So, well, it may sound correct. It's not exactly true. And that's because the story that I want to tell you today largely arises from the lack of clarity in introducing certain formal concepts and not noticing some tacit assumptions of our physical theories. So this project, and also this presentation is a part of my broader project in the center here, is based on an observation that only after we reintroduce these concepts very, very carefully, starting from a formal level, we'll be able to discuss their significance. And today I want to discuss, in particular, epistemic significance. So that's the structure of this talk. I want to talk about 2 types of space-time properties, because this is actually one of the formal omissions, as I want to call them, that appear in the literature about space-time and its epistemology. So I argue that they are in particular 2 types of space-time properties, metrical and topological. And then moving to the discussion of their epistemology, I will distinguish between 2 types of facts that are epistemically relevant here, which are evidences and tests. And then I'll conclude with some brief discussion of how these findings may find its place in the broader philosophical context. Okay, so what are these various levels of manifold structure? When I first introduced a manifold a few slides before mentioning the light cone structure, I was talking about the topological structure, which doesn't yet include any notion of distance, but provides continuity and therefore distinguishes holes. So the most canonical example of a topological property, or 2 manifolds that are topologically distinct, is a torus and a sphere, because a torus, a donut, has a hole, a sphere doesn't have a hole. And it was only after we added a metric to that structure that we could begin to talk about distances and also about time-like, space-like, and null vectors. And for the rest of this talk, I will focus on these 2 levels of structure. Though one should also note that these are not only levels of manifold structure. We have also affine structure, differentiable structure, but that's not very relevant to the talk today. So accordingly, you can talk about 2 different types of manifolds. So first, there is a topological manifold, which unsurprisingly is a manifold equipped only with a topological structure. And examples include a sphere, a torus, a Euclidean space, Rn, a Mobius band, or a Klein bottle. A Klein bottle is basically a Mobius band or an equivalent of a Mobius band in 3 dimensions. And then there is a metrical manifold, which is a manifold with metrical structure defined on it. And the examples include here the aforementioned Free-Poisson Lorentzian manifold or Minkowski space-time from special relativity, and so on. Now, since metrical structure builds on topology, but not vice versa, all metrical manifolds are topological manifolds, but again, not vice versa. Now, all of this might sound like something taken straight out from a physics handbook, But these levels of structure already give rise to deep philosophical questions. And just to give you one example, think of one of the most famous debates in philosophy of space-time, the whole argument, which originated from Einstein himself and then further was developed here by John and Professor John Earman. So one way of thinking about this argument is that it is a debate about the relation between topological and metrical levels of space-time structure. Okay, so for us in this specific talk, this distinction is important because it gives rise to two types of space-time properties, topological and metrical. Remember, this talk is about testing space-time structure, that is testing space-time properties. So thus, we can ask, what are these space-time properties? What are examples of space-time properties? So again, we'll have the distinction between topological properties and metrical properties. And topological manifolds can be Hausdorff, bar-compact, simply connected, locally simply connected, and so on. And metrical manifolds can be geodesic complete. They can have different metrics. For instance, 3+1 Lorentzian metric. They can have causal structure, and so on. Now, most of these space-time properties are quite abstract and hard to visualize, especially if you don't work with mathematics on your day-to-day basics. And let's consider the example of the Hausdorff condition. It is a topological property that says, roughly speaking, that you can separate any two distinct points in space-time using known overlapping neighborhoods. So it is quite hard to visualize it, I think. But luckily, there is at least one space-time property that has a more intuitive interpretation. And thus, to address the key question of this talk, how to test space-time properties, I will use the example of space-time orientability. Before I explain to you what I mean by space-time orientability, let me just say that in this sense, this presentation is a part of a larger project, namely a revival of the discussion around space-time epistemology, which has been somewhat neglected in recent years in favor of debates of space-time metaphysics. And for instance, all of you probably have heard of the substantivalism versus relationalism debate, both in a historical and contemporary version. I just mentioned the whole argument, but you may struggle to recall what is the most recent debate on space-time epistemology. Historically, though, space-time epistemology has been a rich area of inquiry. And for instance, you may know works of Helmholtz, who asked which of the many candidate mathematical geometries represent the physical structure of space and time, which normally nowadays is called as the problem of space. And further, you're also probably familiar with works of Poincare on conventionalism or Reichenbach, who discussed the epistemological implications of living in a toroidal space. Further, more recently, we've seen work by Lemke, who coined the term of space-time theories, and seeking to establish their classification. He also acknowledged that it is possible to have some space-time structure that yield the same observational results. However, I think that what is still missing from this picture is a systematic debate on space-time epistemology after GR, especially the one that takes seriously the distinction between various levels of manifold structure, as I mentioned before, topological and metrical. And in particular, even when we look at the history, such philosophers as Helmholtz or Poincare were primarily concerned with curvature, in other words, with metrical properties. But there are many more structural levels to consider, and as we shall see, each raises its own epistemic questions. In the case of this specific talk, I mean topological properties. All right, so how should we understand orientability? And I think that everyone has some intuitive grasp of this concept. So we can think of orientability as a space-time property that gives rise to something like handedness, a distinction between left and right, whatever that means. And thus we can make a simple observation from our everyday experience, which is that left gloves don't fit right hands and vice versa. In other words, you can't superimpose a left hand on a right hand. So we can say that it is an objective, or rather that there is an objective distinction between left and right. In other words, handedness exists. And from this intuitive notion of orientability, we can conclude that our space-time, that is the space-time that we live in, is orientable. Lovely. So does it mean that we can all go back home because we've already found our empirical evidence? No, that would be too easy, as you can expect. And this is because if we look at the solutions of Einstein equations, widely considered to give us a set of at least in principle physically possible spacetimes, we will find such solutions as Klein-Bottle, which are not orientable. How is it then possible that our everyday experience doesn't seem to allow for this possibility of living on a non-orientable spacetime? And perhaps it is precisely this experience that should make us conclude that, while Klein-Bottle is compatible with Einstein equations, is that not describe our spacetime? As it turns out, one does not have to exclude the other. And this is why, when it pays off that we so carefully introduced our definitions of a manifold at the beginning of this talk. Because even if we live on a non-orientable space, like a Mobius band, we can still locally distinguish two types of hands. And that's because the Mobius band, as every manifold from its very definition that I introduced, is still locally homeomorphic to a Euclidean space. And since Euclidean space is always orientable, we can still at least locally distinguish between left and right. And a note, obviously I say left and right in brackets here, because this notion of left and right is not consistently defined across the whole manifold. And thus, to conclude, on the basis of our everyday experience, we cannot definitely say that we don't live on a non-orientable manifold. I think it is a good moment to explain why I chose orientability as the example of a space-time property, which epistemology I want to explore with you in this talk. And earlier I said that this is because orientability is relatively easy to imagine, unlike, for instance, the Hausdorff condition. And it is still true, but there are also deeper physical and philosophical reasons for this choice. And first, in the physics literature, it is usually assumed that space-time is orientable. And this assumption most often appears as time-orientability in the context of GR. But while this property is commonly assumed, it does remain unclear whether this is a simply matter of convenience for physicists or whether it's based on some empirical grounds. And to just give you an example, if spacetime is not time-orientable, so if we don't assume this, then we can't define certain notions like a causal structure. So it does make sense that physicists would assume orientability. However, I believe that as philosophers, we should press on and ask, is this assumption of orientability merely an assumption made for the sake of calculationism or a theoretical consistency, or is it a genuinely empirical fact of our universe, one that we've tested or at least could in principle test, or we at least intend to test? And we'll get back to these questions later at this talk. And second, orientability, while it hasn't been discussed by philosophers as interesting on its own, is usually employed in philosophical debates that concern the notion of incongruent counterparts, and are related to this famous argument by Immanuel Kant against relational space. This argument treats on space-time metaphysics, and for this reason, I don't want to go into much details, because as I said before, what I'm trying to do with this talk is precisely to depart from the debate about metaphysics and move in the direction of epistemology. But I think it's still interesting to see why is it still worth testing such a property of spacetime as orientability, and how can it inform our philosophical disputes. So the argument roughly goes as follows. That's Kant, not me. Don't blame me for it. First, assume that space is relational. Kant will try to reduce it ad absurdum, so that it consists merely in primitive spatial relations between objects that constitute it. And now imagine that a human hand comes into existence in this otherwise empty space. This hand, Kant continues, has to be either a left hand or a right hand. However, if space is relational, then this hand is neither left nor right. And that's because in relational space, only the relations between parts of objects matter. So when you look at your hands, the relation between this finger and this thing and this finger and this finger is exactly the same for both types of hands if you don't have anything external in space, with reference to which you can test its handedness. So finally, to conclude, Kant argues that spacetime is not orientable. That spacetime is not relational. However, one of the ways to argue against Kantian argument, or rather undermine it, is to just say, well, if space is not orientable, then point 3 fails. Because as we've seen before, on a Mobius band, a hand doesn't have to be neither left nor right. I just mentioned a few authors who employ orientability in their arguments against Kant. I'm not going to go into the details of this also because their treatment is quite superficial, but just to tell you what is at stake, like we can argue for, or like we can defend relational space if we actually can prove that space is non-orientable. All right, one note here is that in this philosophical literature, and largely in the physics literature that I've briefly mentioned before, there are like various types of orientability are confused. So I've already signaled that I'll be talking about topological and metrical properties of spacetime. And orientability is a lovely property because unlike any other that I can enumerate, it does have these two versions. It exists on the level of topology and on the level of metric. All right. And actually, let me note one more thing here. So, I was just blaming philosophers for confusing two types of orientability. But actually, I also deliberately make this mistake just 2 slides ago when I showed you a Mobius band with 2 hands on it. So there are actually several things that are wrong with this example. The first one is that the Mobius band is 2-dimensional surface embedded in 3-dimensional space. So you can't have 3-dimensional space on this manifold, but that's not a very good point. But beyond that, I want to suggest that there is a more profound issue with using this kind of an example that comes up in this literature to explain orientability. And in particular, as I'll argue later in this talk, hands are not appropriate for testing the kind of orientability that the Mobius band lacks. And in fact, it is in principle possible, as we'll see very soon, to have globally well-defined handedness on a manifold that fails to be orientable in the same way in which Mobius band does. And this is because, as I've argued in my earlier work that I actually cite here very shamelessly, and as I'll show you in the next few slides, there are actually 2 distinct types of orientability, and you can prove mathematically that they are at least partially independent. Don't worry, no more mathematical proofs forthcoming. All right, so what are these 2 types of orientability then? I already made all spoilers that one lies on the level of topology and another one is metaphysics, but let's try to define them. So the first, we have something that I call manifold orientability, which is a form of orientability defined on the topological level. And I'll be very honest with you, these definitions are not very intuitive if you don't really work in topology. So one of them builds on non-vanishing n-forms, and another one builds on, which is equivalent to the former, builds on the notion of transition functions that are orientation preserving. And I gave you these examples not only to keep, rigorous character of this talk, but also I think that the difficulty in explicating these types of orientability in more intuitive language will prove to be one of the difficulties later on when I suggest certain tests for this specific type of orientability. And this is because in this specific case, we think about the purely topological manifold, but the manifold that we live in is metrical. So this type of orientability, we don't really have around us the types of mathematical properties or like entities that are employed in this definition, such as n-forms and so on. So just to understand what this type of orientability is, let me just use examples, because actually the examples that are familiar to you, like Mobius band or Klein bottle, fail to be orientable in this specific sense. So topological orientability, called here manifold orientability, is the one that is associated with such examples as Mobius band or a Klein bottle. All right, good news is that metrical orientability is much easier to depict, I think. And again, in order to understand it, it will pay off that we introduce definitions of various types of vectors at the beginning of this talk so carefully. In particular, given that metric gives rise to time-like and space-like vectors, we should rightly expect two corresponding types of orientability, that is space and time orientability. And as we see that in particular, 3+1 Lorentzian manifold is time-orientable if and only if there exists a continuous non-vanishing time-like vector field on it, and correspondingly it will be space-orientable if there exists a continuous non-vanishing field of triads of orthogonals, that is perpendicular space-like vectors on it. And why do I say that it is easier to depict this intuition? Well, because both time-like vectors and a triad of orthogonal space-like vectors resemble objects that are familiar to us from ordinary life, such as hands or clocks. So I'm thinking here about if you do this with your hands, it gives you kind of a real-world equivalent of tetrad of orthogonal vectors, and you can see that you can't superimpose it. You may remember this from your physics classes. Okay, and just to clarify, I'll say that spacetime is spacetime orientable if it is both space and time orientable. So just as in the case of manifold orientability at the topological level, we can also come up with equivalent definitions of time and space orientability. And I'm doing this because they will prove to be extremely useful when we talk about epistemology and tests for spacetime orientability. So in particular, you can define time orientability in terms of a parallel transport of any time-like vector along closed curves that come through some fixed point that do not change its orientation. So in particular, if you can find a point and consider all closed curves that go through this point, like let's say that this is your point, you consider all closed curves that go through this point, such as this one. If you can drag, let's not go into the details of the notion of parallel transport, you can imagine this as a dragging, for instance, a time-like vector along this curve. If the orientation is not changed, then this is a time-orientable manifold. And this is an example of a loop that doesn't change orientation because we can find a continuous vector field according to the previous definition, and according to this definition, it doesn't revert our orientation. And similarly, we have the same definition, but in terms of space-like vectors. And here we see that there is some kind of flip here. So we are moving from left hands to right hands. So that's an example of a loop that actually reverses orientation. So if you find such a loop on your manifold, you know that it is not space orientable. All right, so to sum up, manifold is orientable if there are two classes of handedness. And for instance, I say handedness in brackets, because for instance, for spacetime orientability, we have left and right, and for time orientability, we have future and past. And by this, I refer respectively to orthogonal triads of space-like vectors and then to time-like vectors. However, in order to know which class is which, for instance, which triad of orthogonal space-like vectors is left and which one is right, we need something more. And this extra property is called an observation. So far, why do we need this property called property called orientation? So you may remember from the definitions I just discussed just now, orientability is defined as a vector field, and then orientation is a choice of this vector field. So orientation will tell me that I do have two incongruent hands that I can't superimpose. Orientation will tell me it is God-given that this is a left hand. Okay, So you may wonder, why do I introduce even more definitions? And this is again because thanks to the carefulness with which we introduce all these types of orientability and now orientation, we can examine the relations between these various types of notions, which, as I said before, in the literature are often confused. And for instance, just by looking at the definitions of orientation or orientability, you can easily observe that if space is spatially oriented, then it is also spatially orientable, and same applies for time orientation and time orientability. It is a fairly intuitive conclusion. However, more interesting cases concern the relation between manifold orientability at the topological level and spatial and temporal orientability. So how do these relations work? So first, let us consider an example of time orientability without a manifold, namely topological orientability. And now, because metrical orientability and topological orientability refer to different levels of manifold structure, you can have a manifold that is non-orientable topologically, for instance, a Mobius band, but on which you can define a continuous time-like vector fields. Now, I'm not saying yet anything about epistemology. I want it to be clear. I'm only saying that in principle, it is possible to define such vector fields on certain topological manifolds. And in fact, the reverse also holds. So you can think of a manifold that is topologically orientable, for instance, the cylinder that you can see here, but which fails to be time orientable. That's an illustration showing that we have some kind of lack of continuity. The time-like vector flips. So now, does it mean that there is absolutely no relation between topological orientability and metrical orientability? And that's not true either, which makes this whole story even more interesting. So in particular, if you consider a 3 plus 1 Lorentzian manifold, and the conjunction of time orientability and space orientability, it follows that you obtain a manifold orientability on a topological level. However, one should note that reverse doesn't hold. And in particular, you have a topologically orientable manifold as the one on the picture, and it can still fail to be time and space orientable, which you can see here by the choice of various types of vectors within these tetrads. And note that it is a fairly big result, because not only it shows us that there are two types of orientability, which are often confused in the literature, but also that they are, at least to some extent, independent. And as we'll see very soon, even though these considerations may come across as tedious, they will be really useful when discussing epistemology. Okay, so we finally arrived to epistemology of the space-time properties. Okay, so again, big picture. What would be your reaction if you were confronted with the question of how to test empirically space-time structure? And it seems to me that the most common answer would go something like this, what I put here on the slide. Go learn some physics, read some handbooks, study GR, study the standard model of particle physics, look around, do some experiments, gain everyday experience, and you get your answer. And this works because, as I have already briefly mentioned before, and I will elaborate in this section, certain space-time theories presuppose certain space-time properties. And in particular, this type of question refers to our space-time, in which we have all these theories, such as the standard model of particle physics. However, there's also a different type of question, which historically has been asked by various people. So in particular, you can also ask, in a hypothetical space, if you live in this, can you actually test its properties? So here I give the example of flatland, which obviously was historically formulated in a different context, but it is a perfectly legitimate question. You can ask how a hypothetical imaginary flatlander tell that they live on a flatland rather than in a higher dimensional space. And based on this observation, I think it is helpful to introduce the following distinction between evidences and tests. So first, let us turn to evidences, and let's introduce the following notation. So let P be a physical property that we want to test. So in other words, we want to ask whether our spacetime has the property P, and then let E denote an experiment and C a physical theory. And now I want to think of evidences as arguments from existing and experimentally verified physical theories, assuming a spacetime property that we want to test. And using the notation that I have just introduced, we can say that an experiment E tests a physical theory T, and that this physical theory assumes the property P. That's the general scheme of how I want to think about evidences. And as we shall see very soon, an experiment can be either understood as everyday experience or some lab experiment. For instance, some experiment confirming the standard model of particle standard model of particle physics or GR or whatever. So given that for evidence, we need a physical theory, which usually involves some kind of dynamical field of our spacetime, inherently, evidences can be employed only to test properties of our spacetime that we live in. So we can think of the following dialogue in the context of evidence. So someone may ask, is our spacetime orientable? And then the answer will go something like follows. Let me check whether the standard model of particle physics, thermodynamics, cosmology, and so on tells us something about this. So since these theories are empirically confirmed by various experiments, we conclude that spacetime have property P, as long as obviously they assume this property P. Second, we can also think about tests of certain spacetime properties. And I want to here understand tests as designs of experiments with the purpose of testing certain spacetime property from its very definition. And now, again, using the notation I developed earlier, you can see that I drop the element of physical theory here. So in the case of tests, we have only E and P. And again, we can think of an analogical dialogue of a torus lander. The difference here is that here we are talking about epistemology of any spacetime. In particular, it can also be our spacetime. Okay. Now, I acknowledge that some may argue that the line between tests and evidences, as I define them, is quite fine. And to be fair, I'm in this group. So for instance, you can say that there is no such a thing as experiment directly testing a certain spacetime property, because every test is still mediated by some physical theory. You can't design an experiment without any physical framework at all. And at the same time, going the other way around, one may argue that some evidences are based on definitions, as we shall see in the examples below. Again, like if you want to run what I call an evidence here, you always, in order to conclude that you've tested certain spacetime property, you do have to look at its definition. So here I made this distinction for 3 reasons. So first, I have always been encouraged to endorse this distinction by people with whom I shared my research, because it seems to reflect the idea that physicists normally talk about evidences. So when you go to a physicist and you say, is spacetime orientable, they would obviously say, oh, obviously spacetime is orientable because we need orientability to have the standard model. Or, of course, spacetime is time orientable because you need to have it to have causal structure in GR, and so on and so forth. But again, it seems to me that there is still room for asking, can you actually go and directly test it in the same way in which you've built CERN to find Higgs boson? Can you build a CERN to test certain spacetime properties? The second reason is because introducing this new type of evidences that is not usually widely acknowledged in physics, that is tests, we can talk about orientability of a spacetime, like of any spacetime or of any space, which extends this debate in an interesting way. And finally, the third reason for making this distinction is, as we shall see by the end of this talk, there are different types of limitations of both tests and evidences, which I think that makes them interesting in a non-trivial way. Okay, going to the meat. So let's consider some examples of evidences of spacetime orientability. So first, we can consider evidences for topological orientability. And the example that we'll consider here is the existence of fermions. And the examples for metrical property will include the arrow of time and parity violation. Note that I'm not saying that this is the final, ultimate, complete list of evidences that you can use to test spacetime properties. I'm just saying that these are examples that usually come in the literature. Okay, so let us start with the first example, which concerns topological orientability. So that's the setup using TEP. And the argument is quite technical, and don't worry, I won't go into the details, but the general structure goes as follows. So first, observe that there are plenty of experiments, such as an experiment E that confirms theory T, and T is here the standard model of particle physics, and E is any experiment run in CERN. Go and find your favorite experiment that confirms standard model. Then, according to the standard model, we observe that the evolution of systems with fermions is described by the Dirac equation. But then Dirac equation, you can prove it, that's the common belief in the literature, the Dirac equation in curved spacetime requires the notion of tetrads. And tetrads are here understood as 4 linearly independent vectors defined at each point of spacetime in question. And roughly, you can think of them in the same way in which you thought about the orthogonal triads of space-like vectors when you've talked about space orientability. But here, because you don't have metric, like all of these vectors are of the same kind, and obviously they don't have any account of measures. And now the next step is that tetrads can be defined only on parallelizable, manifolds. I was trying to learn how to pronounce it. And then further, you can argue that all such manifolds are topologically orientable, and hence our spacetime manifold is topologically orientable. Okay, what can go wrong with this argument? I can already tell you that the structure sounds sound, so we can reject it only by questioning one of the steps. And actually, you can do this. Because what if I tell you that we do not actually need tetrads to write down Dirac equation in curved space? And it can be actually done, as has been shown by 2 Russian physicists in the 60s, who introduced the formalism of spinors. And later on, recently, some philosophers like Pitts show that spinor fields are defined directly in terms of the metric tensors without the need to introduce tetrads. And so step 3 from our previous argument is incorrect. So the manifold doesn't have to be such like this. And one can conclude that, therefore, the empirical success of fermion-based theories, like the standard model, does not entail that spacetime is topologically orientable. And let me just note that this is a pretty big example, right? Because such authors like Penrose or Garrock in their arguments, in their papers from the 60s, 70s, 80s, quite often have this one line in their work saying, oh, manifold is orientable because we do need it for tetrads. But what we did here is that we actually looked step by step through this argument, and by showing elsewhere in other papers how to prove it in a rigorous way, we found that, well, in fact, you can reformulate this whole argument without this tetrads. So you don't actually need to have orientability. For a formal argument, yeah, I'm shamelessly just promoting myself. Okay, so that was the argument for time manifold orientability. How about time orientation? So that's another example that comes up a lot in the literature about orientability. That's the example here is the arrow of time. So obviously in the literature, you have a lot of various evidences, alleged evidences for the arrow of time. I chose here to talk about thermodynamics. Go and find your favorite reason to believe in the existence of the arrow of time. So the argument would go as follows. Entropy does not decrease in quasi-isolated system, and so the direction of the increase of entropy designates future. Fair enough. We've just observed that our manifold is time-orientable. However, my response to this would be that it is likely that the increase of entropy in the observable region of spacetime is only local, and it's just a fluctuation from the perspective of a larger universe. And this is actually not just me, it's already Boltzmann in his original paper. So in particular, while we can have an entropy which doesn't decrease at every point of the manifold, as we can see on this picture, there is nothing in this theory that tells us that it has to hold globally. So here again, we've been too quick with reaching our conclusion. Obviously, also, the era of time comes with its own lots of issues. One of them being, the need for carefulness in distinguishing the asymmetry of time and asymmetry in time. Asymmetry of time won't help us here at all, because we are talking about the most, deep basic level of manifold structure at the topological level. Just to note, because I've briefly mentioned this, another example that people mention in context of time orientation is also the existence of causal structure. I won't go into the details in the interest of time. And now, probably those of you who are familiar with the Kantian literature immediately thought about this example for space orientation, which is based on the famous Wu experiment. So in that experiment conducted in the 50s, Wu and her collaborators were testing the weak nuclear interactions and whether they respect parity symmetry. So you can think of this roughly as trying to answer the question whether laws of physics, whether or not you believe in them, are the same in mirror reflected systems. And to do this, they conducted such an experiment. So they've been looking at the decay of cobalt-60 nuclei, which emit electrons during their radioactive decay. And it actually turns out, again, without going into much detail, that nature in this way does distinguish between left and right. So the particles were emitted statistically more often in one dimension. Okay. However, as I said before, even though this argument comes up a lot in this literature about Kantian argument, that argument, as I presented to you, treats about orientability, while here we have parity violation. And I do think, again, that this move from parity to orientability is too quick. And actually, this whole research, this whole project orientability was inspired by one line from Hawking and Ellis, who said that if one believes that the non-invariance of weak interaction, namely the Wu experiment under certain parity, reveals is not merely a local effect, but exists at all points of spacetimes, and and so on and so forth. It doesn't matter. I don't want to confuse you with what they say later. But what was really interesting for me was the word "if" here, because what people were taking for granted, it seems that can be questioned. And indeed, again, you can think that at every point of your spacetime manifold, you run your Wu experiment here and here and there. You have these preferred direction in space, but there is nothing at the level of this experiment that tells you that this holds globally and that this vector field is actually continuous. Okay, so what are the limitations of evidences of space orientability based on these examples and based on what, some other observations? So first, limitation I want to mention is quite provocative. And I called it, the pessimistic meta-induction. So according to this argument, because our past theories turn out to be incorrect, we should not assume that our current theories are correct. So even if you believe that, if you have the standard model, it entails manifold orientation, the standard model can be incorrect. Therefore, you should not make this interference about about manifold orientation. Another reason is, well, it can turn out that the experiment E does not confirm theory T. It does happen in the history of science that we observe certain things. We think that this result confirms our theory, but actually it turns out that it doesn't. I know, like think ether theory, Michelson-Morley experiment, and then Lorentz thinking that this is, a confirmation of ether and contraction. And another reason can be that an experiment in E indeed confirms some theory T, but this theory T can be reformulated without assuming the interesting property in question. And that's the example of the standard model and tetrads of vectors. You don't need tetrads to have the standard model. And finally, I just wanted to add that, our experiments can be incorrect. I don't think we give enough attention to this fact in the philosophical literature. Okay, so now when we came to this pessimistic conclusion that evidences fail, let us move to my brand new project, which are tests for space-time structure, namely those more direct ways of observing space-time structure. So, I introduced tests as designs of experiments. So when you were asked to design an experiment in physics, during your lab class, how would you start? Well, I think that the starting point would be always to choose some kind of probes. And actually, I already hinted at this probe. So you remember when I was introducing the definitions of time and space orientability, I was talking that you can think of tetrads of vectors as hands, tetrads of orthogonal space-like vectors as hands, and then time-like vectors as clocks. But at that time, I only mentioned this without justifying it. But actually, when you think about this, that's a very fair intuition here. So it sounds that they are very good examples for testing our space and time orientability. Okay, so what should I do with these probes in order to test our space-time orientability? Well, I need to, do something with them, and in particular, I probably should send them, in some journey during around space-time. And why is that? This is another moment when, introducing very carefully definitions for space and time orientability pays off. So you remember I introduced the first definition in terms of vector fields. But how on earth are you going to test vector fields and whether there exists a consistent vector field on a manifold? Like, after all, like if this sounds abstract to you, that's not you, that's physics. Like, you can't go to this point and look whether there exists a vector field there. It's not how it works. So then I said that actually there is an equivalent definition which involved travel or parallel transport along closed curves. So there we go. I said that tests will involve experiments based on testing space-time properties from their definitions. So that was your definition. Now we can use it. So we can take our hand or a clock and drag it along closed curve in space-time. But again, as you remember from the beginning of this talk, massive object can travel only along time-like curves. So you see our setup of an experiment starts clarifying. However, there is a little problem with this because traveling along closed time-like curve means coming back to the exact same point in space-time, which is not ideal because even if you stand in one place, obviously your time coordinates change, whether or not you believe in the passage of time. So there is a clever way out. That's my clever way out. So imagine that you are in a lab at point P and you have two hands that are congruent. Right now, you can't tell yet whether they are both left and right because you don't know whether your space is orientable, so you don't know whether its notion exists. And one of your hands stays in the lab, that's this hand, and another one is sent around the whole space-time. And in this specific example, they reconvene at point Q, and you can see that they came back with reversed handedness. So what's the moral? Well, this space is definitely not orientable. What if we have a different result? What if the hand comes back with the same handedness? Does it mean that we've just proven that our space-time is orientable? Wouldn't that be great, right? Well, sadly, no, unfortunately. Why is it the case? Well, again, if you remember our definitions carefully, we need to test the parallel transport of triads of orthogonal vectors, or time-like vectors, or hands right now, along all time-like curves. And because our space-time is quite large, there are quite a few such curves. I mean, like this curve, this curve, this curve, the curve from here to Gdańsk, and so on and so forth. So that's plenty, but actually, if you remember the definition, you can just test all curves that come from one fixed point. But then it's not very helpful because we still have probably infinitely many such curves. So again, this is my favorite point, a curve like this, curve like this, curve like this, and so on. However, again, if you learn your maths, you will actually be able to prove that you only need to test homotopic curves, namely curves that you can continuously transform into one another. That's the formal definition. So again, what should be your intuition about this? If you think about a manifold, about a Mobius band, if you just take a tiny bit of its surface, It does not revert orientation, right? Because it, again, locally resembles Euclidean space. And the problem only occurs if you go through the whole space-time. Even if you go through the whole space-time and don't close this loop, but just before you are going to meet your starting point, you turn back and go back to the original location, it is still a loop that will not change orientation. So in case of Mobius band, we have two classes of homotopic curves. Great, so now instead of testing infinitely many curves, we have only two lines that we need to curve. Great, problem fixed. The problem is that we don't know which curves are homotopic. Like again, if I draw a Mobius band, I can show you which classes are homotopic, but if I live in this space, I can't just go around and think, oh, is this line homotopic to another one? Further, we have a technical difficulty. So you can think that some of these loops can be difficult to travel to because either they are far away. Think, if my one orientation reversing loop is in Proxima Centauri, it's super unlikely I'll find it. Or maybe they're, in very non-accessible places like the bottom of Mariana Trench. But, that's not too bad because we can deal with technical difficulties. Maybe at one point of, the mankind development, we'll be able to go there and find it. But actually, there are also physical difficulties. So in particular, our orientation reversing loop can be smaller than the Planck length and hidden at the bottom of Mariana Trench. It's very pessimistic. Further, maybe our loop is hidden behind the horizon of events. Again, physics tells us we will never be able to send our hands there. And actually, something that I was assuming here all along in the setup of the experiment, that we will send our hands along time-like loops because they're massive objects. But there is nothing in the definition of space orientation and orientability which tells us that the orientation reversing loop has to be time-like. It can be space-like, and we can't travel along space-like loops. Great. So we've been sitting here for nothing, in other words. And actually, if you thought that this is pessimistic, let me finish with the example of testing manifold, namely topological orientability. So again, so far I've been talking about clocks and hands, which referred to metrical orientability. However, what about topological orientability? How can we test it? And again, you can go through exactly the same story. So you can tell the story about the loops, you can tell the story about the vector fields, or in this case, we don't have vector fields, so about n-forms. You remember I said this is very counterintuitive, but also there is nothing in the actual space that has a natural interpretation of this. So here I don't want to go through the whole thing again. So here I just want to dwell on the question of what can we use as our probes? And if we are going to test topological orientability of our space, we would probably think of something like tetrads. But in our space-time, again, we have metric. Like we can't just scrap off metric from our space in the same way in which I can't just get rid of laws of nature, whether or not you believe on this. In other words, you can't get rid of dynamical fields for our space-time just because I want to test certain space-time property. So in particular, when I am to develop the notion of tetrads or use tetrads as probes, these would have to be tetrads of rods. But again, like rods have some kind of length. They are inherently metrical. So it's very unclear of how that would work. So just to finish with something positive, I think that because, again, of our mundane work of proving various relations between time and space orientability, you can prove manifold orientability in such a way that you use this relation, which I haven't proven, but I've proven elsewhere. Great. So just to summarize, I think that maybe this talk was underwhelming in that, the main title was Spacetime Epistemology, and I spent an hour talking about one particular space-time property, which is orientability. But that was a very fascinating type of space-time property, because first it showed the difficulties with testing example of properties that are topological and metrical. Like you see, I was trying very hard to talk about tests at the level of metric. But when it came to topology, I just said, well, it's very unclear what the probes would be. How would we even go about this? And in the broader picture, what I do in my project here is that I try to examine in such a careful way other space-time properties like simple connectedness, local simple connectedness, and so on, to try to see whether first there are any evidences that again have some tacit assumption that you can undermine. Go, see the example of parity violation, see the example of the standard model and topological orientability, and also try to give a try to the probes and see whether there are actually any ways in which you could, in principle, define properties of, you could define tests for topological space-time properties. Thank you.
We take a 2-minute break and then we'll have time for questions.